We're going to talk about 3.3 and 3.4, which is determinants.
And then also notes. Don't use the simple
So,
Use your mouth.
we've seen determinants in the past. When did we do the second derivative test? What class was that?
Last class.
241, like the last class. Okay, so in that class, we wrote down this matrix H that was fxx, fxy, fyx, fyy, and then we calculated this weird quantity d, which was the determinant of H, which was fxx, fyy minus fxy squared, right?
Yes.
What we were actually computing when we did that. So this is the first time we saw a determinant used probably for anything. And remember that like the second derivative test broke into cases, right? There was d is negative, d is positive, and d is 0. And this case was sort of the undetermined case where you couldn't figure out what was happening. What we were actually computing when we did this was, is the Hessian matrix invertible? That is what we actually were doing when we did that. So there's an interpretation for this matrix being invertible. Essentially it means that the function behaves well locally. So the point of determinants generally is that they tell us when matrices have inverses. So I'm not going to tell you how to calculate it yet, but I think this whole discussion will be guided by the fact that this theorem, which has the following. So if A is n by n, so this is only a theorem about square matrices because it's a theorem about inverses. If A is n by n, then the determinant of A is not equal to 0 if and only if. This is a mathematical construction that means if one of them is true, the other one always is, right? Determinant of A is not equal to 0 if and only if A is invertible.
So otherwise it equals 0 if it's not invertible.
That means if it is 0, it's automatically not invertible, right? So the determinant for all the rest of the stuff that it does, where it calculates things like areas and volumes, the determinant is a function that you feed it a matrix and it spits out a number, and what that number tells you is if the matrix has an inverse. That's what the determinant is for. In many applications, and the determinant is widely used, in many applications that is the thing you care about. The determinant has more information in it than that, but for our purposes, this is what we care about. Determinant not 0 if and only if A is invertible. So, we already know how to compute some of these guys. So, I'll give you a couple of easy cases of determinants we already know. So, if I have a matrix A and it happens to be a 1 by 1 matrix, then the determinant of A is just the entry. And it's not hard to see that a 1 by 1 matrix has an inverse if and only if that number is not 0, right? Because 0 doesn't have a multiplicative inverse. Every other number does. So for 1 by 1 matrices, the algorithm is really easy. For 2 by 2 matrices, A11, A12, A21, A22, the determinant of A is equal to the number A11, A22 minus A12 times A21. And I want to point out that this is not some you might ask, why is it the case that that number tells you if a matrix has an inverse or not? I mean, that's easy to compute. If I wrote down something like 1, 2, 3, 4, and I calculate the determinant of that matrix, and I get 4 minus 6, which is minus 2, okay, why does the negative 2 showing up there tell me that I can row reduce that matrix to the identity matrix, or that it has an inverse that I can compute? And the answer is just a calculational answer. So at least in this case, if you wrote down the augmented matrix A11, A12, A21, A22, and over here you put 1, 0, 0, 1, if you can get that matrix on the left-hand side to row reduce to the identity matrix, so if you actually go through the steps of row reducing this symbolic formula, and you get all the way down to this, you will end up on the right-hand side with the matrix 1 over A11, A22 minus A12, A21 times D minus B minus C, A. This will be what pops up on the right-hand side. And of course, this only makes sense when that number isn't 0, so I don't divide by 0. So the initial discovery of the determinant, if you like, can be thought of as, I really want to know a general formula for 2 by 2 matrices. If I try to calculate them, I get this fraction. If that fraction had a 0 on the bottom, it wouldn't be defined. If you actually try to do this and you assume that this is equal to 0, there's a step in here where a free variable shows up. And you can't row reduce to the identity. So the idea of the determinant tracking whether or not a matrix is invertible is written into the formula for the inverse, at least in the 2 by 2 case. And so the big goal then is, well, okay, so I got this number that tells me when 2 by 2 matrices are invertible that's involved in the construction of their inverses. Can I come up with a number that I can attach to any square matrix, no matter what size it is? So, some of you have learned a pretty crazy method for 3 by 3s where you put the matrix down, then you put the rows again, and you write the diagonals and multiply and add and subtract. I want to give a method that goes beyond 3 by 3 and generally works. So the goal now is we want a method for computing the determinant of A for a general n by n. Right? A method that always works for any size of square matrix. And so in order to do that, I'm going to have to introduce a new terminology here. As frustrating as it's going to be, a lot of the things I'm going to say in this section basically turn out to be arguments by combinatorics, which just means lots of symbols flopping around. It's going to be very hard for me to prove that what I'm saying is true. So I'm asking you, at least for the next part of the class, just to accept we're going to build the determinant as a calculational tool, and if you want to know why it shows up the way that it does, you come into office hours and I'll give you a more detailed mathematical argument for this existing. If all you care about is concrete applications, you just need to know that these things exist and what they do. Which for a lot of people, that's enough. Okay, so I'm going to have to make a definition. So given a matrix A, which is n by n, the cofactor matrix of the Aij entry is the matrix resulting from removing the row and column of Aij from the matrix A. Much easier to show you than to write in words. So what I mean is, if I give you a matrix like, let me get my standard example here that I've got rid of in my notes. If I give you the matrix 3, 5, 7, minus 1, 2, 4, 6, 3, minus 2, there's the matrix A. I'm going to show you what the cofactor matrix looks like for the 1, 1 entry. So if I pick A11 is equal to 3, I get the cofactor matrix for A11 by, I like to circle these things. There's A11, get rid of its row and column, and the cofactor matrix is what's left. 2, 4, 3, minus 2. These are going to be the tools that we use, the sort of building blocks we use to compute determinants more broadly. And many of you have actually seen this algorithm, at least for 3 by 3s. Okay, so the actual cofactor, of Aij is called Cij for cofactor. Ij here means row and column. And you calculate it by doing minus 1 to the I plus j times the times the determinant of that matrix. times the determinant of the cofactor matrix of Aij. So it's a number. In the particular example that we've written here, if I want to calculate some cofactors, which are numbers, so you can start with 3, 5, 7, minus 1, 2, 4, 6, 3, minus 2. The cofactor C11 is equal to minus 1 to the 1 plus 1. Then I'm going to take that, delete the row and column, and take the determinant of what was left behind. C12 is minus 1 to the 1 plus 2 times the determinant of, take the 1, 2 entry, get rid of its row and column, and take the determinant of what's left behind. Minus 1, 4, 6, minus 2. I'm going to be using these, which is why I'm calculating them all. And C13 is minus 1 to the 1 plus 3 times the determinant of minus 1, 2, 6, 3. Every entry of the matrix has a cofactor that goes with it. So if I was actually going to finish computing these, minus 1 to the second is 1. The determinant of this matrix, I think, is minus 16 is what that turns into. This is 2 minus 24, which is negative 22, but it's multiplied by negative 1, so you just get 22. This number is 1 times the determinant of this matrix, which is 3 minus 12, which is minus 15. So notice here, we're using our knowledge of 2 by 2 determinants in our attack on calculating these cofactors. So here's the big claim. So I could start by writing this as a theorem, but I'm just going to make a claim instead. If I want a number to assign to that matrix called the determinant, I can compute the determinant of A by det A is equal to A11 C11 plus A12 C12 plus A13 C13. Whatever that number is, I can compute it with this formula. I've worked across a row, and I'm multiplying the entry times the cofactor that I produced with that entry. So in this case, 3 times C11 plus 5 times C12 plus 7 times C13, which is 3 times minus 16, plus 5 times 22, plus 7 times minus 15. And the number that you get out at the end is negative 43. So the point here is, and the theorem says, no matter how I chose a row or column, I would have arrived at the same number. So if instead I had computed this with a different row or column, if I had done A11, C11, and then added that to A21, C21, and then added that to A31, C31, I still would have gotten minus 43.
And this is how you calculate cross product, essentially?
Cross product is basically the result of doing this, yeah. Right. The problem is that, so the cross product is sort of unique because it's a 3 by 3 special case.
Because A11 is the
A11 is the I vector, basically. Okay. And likewise, I could pick any row, or I could use columns. If I want to use the 7, 4, 2, I could write this same thing down as 7, which is the 3, 3, or the 1, 3 position, plus 4, which is the 2, 3 position, plus negative 2, which is the 3, 3 position, and I still would have gotten minus 43. So mathematicians call a number like this an invariant. It doesn't matter how I calculate it. One way of thinking about it is, if you actually wrote down the calculation, these are all ways of describing the volume of the box formed by these 3 vectors. And if you just wrote this down, and you did it linear algebraically, like sort of algebraically, you just wrote down a bunch of symbols and you calculated the volume of those three vectors, no matter how you calculated what the base of the box was, the volume would always be the same. That's kind of what's going on with why we can choose any row or column that we want to produce this number. Now the interpretation of that number, this is one of the things I'm going to ask you guys to black box, because if I start talking about, oh, there's a graded function on the permutations on n elements or something like that, which is really kind of why this all works at a sort of a high-level mathematical way, all you really need to know is that this algorithm lets you produce a number that you can interpret. This number being minus 43, that's not 0. And that means that the matrix 3, 5, 7, minus 1, 2, 4, 6, 3, negative 2 is invertible. It doesn't tell you what the inverse is, but it tells you it has one, which means one set of techniques can be used with this matrix to solve different equations.
Is that usually a faster way to do it than just using the matrix?
So I want you to imagine like there's this interplay between all, like for some types of matrix, this is very fast. So I'm going to show you a faster method for producing the determinant in just a second.
Oh.
Right? So the first thing is, if you're lucky enough to be looking at a matrix full of zeros, then your life is nice, right? So let's see, 1, 1, 0, 10, 0, 2, 1, 0, 0, let's see, maybe 0, 3, 0, 1, and 1, 1, 0, 6.
And can you like stack these, if that makes sense? Like do as one row, and then you have a 3 by 3, and then you have to do the exact same process for the next.
So this
row?
is going to be a process that's an inductive or recursive process.
Okay.
So I'm actually going to write down right now what they. I could write you the theorem, but it's easier just to show you kind of what's going on here. I want to calculate the determinant of that 4 by 4 matrix. The same exact approach applies. I can write this down as entries times cofactors, but it sure would be nice if I multiplied by 0 a lot. So I could pick my favorite row or column to produce the determinant with. Now, I don't know about you, but there's one that really stands out at me here. Column 3, right? A lot of zeros in column 3.
Oh.
So what would the formula say I'm supposed to do? That would say this should be A13, which is 0 times C13, plus 1 times C23, second row, third column, plus 0 times C33, plus 0 times C43. I just sort of walk down the column and I do entry times cofactor, entry times cofactor. So when you can, you should select something with lots of zeros into it, which significantly reduces the calculation. So let's take a look and see what that would actually be. Well, this is 0, and this is 0, and this is 0. So what's left behind is 1. Okay, what is C23? That's minus 1 to the 2 plus 3 times the determinant of what was left behind when I eliminated that row and column. 1, 1, 10, 0, 3, 1, 1, 1, 6. So notice the 4 by 4 determinant requires that we know how to compute 3 by 3 determinants. This type of process is called recursive or inductive. Right? The idea, or recursive, yeah, so the idea here is I have to be able to reduce my 4 by 4 problem into 3 by 3s, and my 3 by 3 problem is going to reduce to 2 by 2s, right? So I sort of walk my way down the chain. One impression that you might have is determinants are a hell of a lot of work to compute for large matrices, and they are. This is incredibly computationally expensive. And a lot of contemporary applications involving matrices involve making sure that you're working with matrices that have lots of zeros inside of them. That's a type of math called sparse matrices that shows up in machine learning all the time. Because if your matrix is a billion by billion and you want to calculate like a determinant, you gotta have an efficient way of doing it. Okay, we might as well just continue this one because I want to show you guys a big determinant before we start moving on to properties and a better way to compute these. So I'm going to pull this off to the side for a second, this determinant of 1, 1, 10, 0, 3, 1, 1, 1, 6. And then observe that again I'm faced with the choice of which row or column to use to produce that determinant. There's kind of two obvious ones to work with here. What you want?
The first column.
First column? Okay. First column. So if we're going to use this column to compute this determinant, we're going to write down A11C11 plus A21C21 plus A31C31, which is 1C11 plus 0C21 plus 1C31. Oh man, okay, so C11 then is going to be minus 1 to the second times the determinant of 3116 plus 0 plus minus 1 to the fourth times the determinant of, I gotta be a little bit careful here. What's in that entry? 1 times minus 1 to the fourth times the determinant of 1, 10, 3, 1. I think that was what's left behind here. Okay, so what do we get? 18 minus 1, so this is 17 plus...
Wait, did you factor in the negative already?
What negative? This, I'm just calculating this by itself, and I'm going to drop it in over here when I'm finished.
So there is a negative.
This is still there.
Got it.
Right, so I'm just calculating this quantity separately. If these terms were all here, you'd have 4 of these to do. And then you would like get a pitchfork out and carry your math professor out to the be burned on the pyre because I gave you 12 determinants to calculate for one problem, right? Would I do that to you on an exam? No. Are there classes where you'll be asked to do that? Probably. Calculators are really good at calculating determinants. So 18 minus 1 is 17, and then that's a positive 1 times 1. This determinant is 1 minus 30, so like minus 29. So this is minus 12. And then take that negative 12 and drop it back over here, so I get 1 times minus 1 times minus 12, which is 12. Okay, so the point of all this is, these things are useful if you can calculate them, but they're a pain in the butt to calculate. Unless you know the secret trick, which I'm going to show you next. So there's a certain type of matrix that is very easy to calculate the determinant of. So this is a theorem. If A, oh yeah, the zero matrix is pretty easy. If A is upper triangular, then the determinant of A is the product of the diagonal entries. So, for example, 1, 1, 10, 0, 10, 2, 0, 0, pi.
But if you have that, and the only reason we're getting determined is to decide if it is art, does that not have poles?
So there's sort of two parts to this, right? So this would be obviously invertible because it has to, I mean, the part of the theorem is to tell you that if you were upper triangular, like, that, yeah, right?
So you're just saying that upper triangle?
Yeah, so upper triangular, so a lot of like algorithms in practice actually involve taking a matrix and putting it into upper triangular form and calculating determinants. Determinants turn out to be useful for applications beyond just checking for invertibility. So I'm trying to give you a faster way of doing it if you were asked to do it.
Got it. So
Right.
this isn't like, for this class, if we're trying to determine it, you're telling us.
Yeah, for us, generally for us, it's going to be enough to know if, for my purposes, I want you to know if a matrix is invertible or not. For classes that come after this, you're going to be asked to calculate these things, and I'm going to give you a faster way of doing it. Right?
It's a bit, if you ask us like 10 different ways that matrix is invertible, you can say that the determinant is equal to 0 and that it's an upper triangle. Like
No. The upper the upper triangular. This is just if A is upper triangular, then you could just find the determinant by calculating you just multiply the diagonal entries, right?
Okay.
You can connect this up with the invertible matrix theorem. I'm just not doing it yet.
Okay.
Right? So if a matrix is diagonal, you can calculate the determinant just by going, or upper triangular. So upper triangular means all the entries are on the main diagonal or above, zeros underneath. You just go ding, ding, ding down the main diagonal. 1 times 10 times 5. So a question that might be kind of a natural question is, well, if it's so easy to calculate determinants by putting it into that triangular form, can't you just row reduce the matrix first, put it in triangular form, and then calculate the determinant? And the answer is yes, but you have to pay the piper. So let me see what explain what I mean by that. So every row operation has an effect on the determinant. So we're going to write those down. The first is, so 1. This is the swap operation. If A is row equivalent to B, by swapping 2 rows of A, then the determinant of A, the determinant of B is -1 times the determinant of A. If I swap 2 rows, I change the sign of the determinant. 2. If A is row equivalent to B by a row scaling, so this is scaling. If A is row equivalent to B by a scaling, of a row of A by a constant K, then the determinant of B is equal to K times the determinant of A. The way to think about that is if I gave you a bunch of vectors and I stretched one of them out by multiplying it by some number, the volume of the box changes by the same amount.
So if we have a determinant, if we find a determinant and we want to find the determinant of A, we have to do that like
Yeah. Yeah.
or multiply by the determinant.
That's right, no such thing as division. And then finally, for those of you that wondered why I set the third operation up the way that I did, so this is the replace operation. If A is row equivalent to B by the operation some row of A, so like the ith row of A got replaced by the ith row of A plus some multiple of the jth row, as long as I leave that first row alone, so this is the row replacement operation, then the determinant doesn't change. And so these 3 sort of charges for these row operations give us another way of calculating determinants. I'm going to start with a matrix, I'm going to row reduce it until it's upper triangular, and then I'm going to calculate the determinant of what I end, and then I just have to account for how I got there. So let me show you what I mean here. Let's look at the matrix 1, 2, 3, 4. I'm going to call that matrix A. I want to calculate the determinant of A, which I can do right now because I know this formula. The determinant of A is equal to 1 times 4 minus 2 times 3, which is -2. But suppose you didn't know that formula, but you did know that if it could put that into upper triangular form, I could just multiply on the diagonal. Let's put it in upper triangular form. What's the row operation that would do that? A row operation that would do that.
Subtract by -3, like the first multiply the top by -3 and combine them.
Row 2 is replaced by row 2 plus -3 times row 1.
Yeah.
What's the cost of that operation?
No.
Nothing. The determinant didn't change. And we'll be able to see that when we write this down. So if you did that, you get the matrix 1, 2, 0, -2. Notice that the determinant of that matrix is the same as the one we started with, right? Because now I could just multiply the diagonal entries. It's upper triangular. The determinant of this matrix is -2. Suppose you continued because you thought, well, I row reduce every matrix to row echelon form. So I'm going to scale that last row to make sure I got leading 1s. So you do another operation. Row 2 becomes minus 1/2 of row 2. Well, that would lead you to the matrix 1, 2, 0, 1. What's the determinant of that matrix?
1.
That's pretty easy, right? 1 times 1. It's upper triangular, so I can multiply them together. So the determinant of this matrix is 1. So if I want to build sort of an algebraic expression relating the determinant of the output matrix here to the determinant of the input matrix, one way that I could do that would be to say, I started with the determinant of the matrix I didn't know, which is this determinant A. And when I was finished, I had the determinant of the matrix 1, 2, 0, 1, which is 1. But to get from this matrix to that one, I have to account for the row operations that I used. What was the charge for that operation? Multiply determinant by what?
Nothing.
No, not nothing.
Oh, 1.
1, right? Doing the row operation to get me from here to here multiplies the determinant by 1. Doing the row operation to get from here to here multiplies the determinant by what?
-1.
It's the scaling, right? So if I'm trying to solve for the determinant of A, this would mean that the determinant of A is 1 times minus 2, which is minus 2. So this is a much faster way of calculating determinants. I know this is kind of a dumb example because it's 2 by 2, but like, it's a much faster way of doing it. Right? Do the row operation. Let me give you an example that is maybe more relevant to the kind of things we have to do here. Suppose I gave you the matrix, let's see, 1, 0, 1, 1, 0, 0, 0, 3, 0, 1, 2, 0, and 0, 0, 1, 1. And I say calculate the determinant.
3.
Man, you could do that by doing stacked determinants. You pick this row of zeros and you do this like horrendous process. But can you is it an easy way to make that matrix into upper triangular form?
You just switch.
Switch what with what? Remember, each swap induces a charge of -1.
Oh, right.
So,
Swap 2 and or
So these two.
Those two and then swap.
hold on, let's do it. Let's just to make sure we don't blow this. Let's do it one step at a time. That would give us 0, 1, 2, 0, 0, 0, 0, 3, 0, 0, 1, 1.
Then swap 2 and
Swap these two, and that gets you 1, 0, 1, 1, 0, 1, 2, 0. Man, this is a mean test question, but it'd be a funny one.
Why?
0, 0, 1, 1, because it really tests, like, hey, maybe you should consider using row operations here. What's the determinant of that matrix?
3.
It's upper triangular. So we multiply down the diagonal and we get 3. The determinant of this matrix, I'll call B, is 3. What is its relationship to the original matrix? Times -1 times -1, so the determinant of this matrix is the same as the determinant of that. And I'll tell you, this is easier to do than that. Unless you really like doing cofactor expansion. Okay, so determinants are easy to calculate. So the charge here was the determinant of each of these imposed a cost of -1 because they were row swaps. And so the equation that you would write down here would be the determinant of A times -1 times -1 is equal to the determinant of this thing at the bottom, which we can calculate as equal to 3. So row reduction to diagonal form or upper triangular form and then calculating down the diagonal is the most efficient way of calculating a determinant. All right, so there's a couple of rules that I want you guys to know about how the determinants act algebraically that show up in practice. So here's some additional properties. The determinant of a product is equal to the product of the determinants. Remember, these all apply to square matrices of the same size, right? Determinants have to be applied to square matrices. The determinant of a matrix, of the inverse of a matrix, is 1 over the determinant of the original matrix. Okay. And then maybe the most important property that I've left out here is the part of it that corresponds to the invertible matrix theorem. I guess I could point out the determinant of the transpose of a matrix is the same as the determinant of the original matrix. That should, I mean, you should believe that, because if I switch the rows for the columns, then I just calculate the determinant with the row instead of the column and I get the same answer. And then finally, and maybe the single most important one, so this is the sort of like the most important property. If, given A is n by n, the determinant of A is not equal to 0 if and only if A is invertible. And in this case, AX is equal to B. Why am I doing it down here? Hold on. I'll just write it up here. In this case, AX is equal to B has the unique solution X is equal to A inverse times B. This is how this connects up with the invertible matrix theorem. So if your determinant is non-zero, any linear system you're involved with has a unique solution and you can calculate it. On the other hand, if the determinant of A is 0, A is singular, and either AX is equal to B is inconsistent, or AX is equal to B has infinite solutions. All right, so the idea of checking the determinant tells us something about the structure of the solution set to linear equations. Another important part.
Is that B? Never mind.
Where?
That's a B vector, right?
Here?
Yeah.
Or here? Yeah, those are B vectors.
Yeah.
Sorry, my hand's getting tired, so I don't need to like write my sleep. Yep.
So that can mean like it can be a line intersection of all the, if it's like a system of, oh no, because it's just,
No, it means that they have to intersect at a single point.
no, if it's inconsistent. If it's
So yeah, so
not-
basically the way to think about it, if the matrix is inconsistent, it means that you have a whole bunch of like objects where one of them is contained inside some of the others, right? So like if I have a whole pack of planes, but they intersect in such a way where one of the planes is contained in the set that's formed by the intersections of the rest. It's like extraneous information. I give you the same plane twice, right? That would be the infinite solution case. If I gave you planes that don't have a unique point of intersection, that would be the inconsistent case, and both of those are picked up by the determinant. So in practice, you know, like one of the applications of the determinant is precisely this.
Does the determinant equal 0 if there's a single free variable?
Yes. Yeah, because you don't reduce to the identity, you can't row reduce to the identity matrix, which means that if you end up in row echelon form, there must be a 0 on the diagonal because of the free variable, and that forces the determinant to be 0.
What guarantees that it equals 0 if it's inconsistent? Because can't you have the matrix, or because this is only for A? So
Yeah, no, a square matrix, if a square matrix has an inverse, what that means is every input got sent to unique output, and every possible output got hit by some input.
Because even when it was inconsistent and it was like 0, 0, 0, 1, the 1 was in the B vector.
It was in the B vector.
So the A vector still had the whole row as 0.
Yeah.
Okay.
It's that row of zeros is the thing that causes it. All right, so the last thing I want to teach you guys is something that I will tell you that I've not used it as anything other than a theoretical tool in my own calculations, but many classes that people take after this one actually require that you know how to do this. So this is a little bit of weird esoteria called Cramer's rule. Okay, so maybe you decide to yourself, if you're looking at an equation like, I don't know, somebody comes along and says, hey, I'd like to know the answer to x plus 2y is equal to 3, and 3x plus 4y is equal to 6. And you say, well, I've got a bunch of methods for doing that. I guess the first method I might use here would be, I could write down 1, 2, 3, 3, 4, 6, and then row reduce. It's like sort of method 1. The second method you might check is, well, if the determinant of that matrix is not 0, which it's not, that means it has an inverse. And so method 2 might be, maybe you could write down xy is equal to the inverse of 1, 2, 3, 4 times the vector 3, 6. That will be another way of computing the solution, right? So the matrix inverse method. There's a third method. So Kramer's rule says the following. I'm going to write a rule down, and I want you to marvel at like the ridiculousness of like why you should even believe this is true, and then I'll prove that it works. So here's what Kramer's rule says. Suppose the determinant of A is not 0. Consider the equation AX is equal to B. And here I'm thinking of the vector x as being variables x1 up to xn. Then I can find the entry of the answer xi by taking the determinant of a matrix bi and dividing it by the determinant of a matrix A, where, this is where this just seems like, how on earth could this possibly be true? Where bi is the matrix resulting from replacing the ith column of A with the vector B. Much easier to show you, I think.
What do y'all have to, why is the column not the row?
That's what the rule says. So, what would that look? Hold on. I promise.
Oh, because it's squares, so the rows and columns. Okay.
So let me show you like, what this would say. So in this case, how would you actually use Kramer's rule? So we have the matrix A here, which is invertible. It's the matrix 1, 2, 3, 4. And I first checked that the determinant of A, which is 1 times 4 minus 2 times 3, which is -2, is not 0. Okay, I can use Kramer's rule. And also I needed to calculate that anyway because Kramer's rule requires that I divide by the determinant of A. Now I'm going to compute the matrices B1 and B2. B1 is the matrix you get from A by replacing column 1 of A with my solution vector. So 3, 6, 2, 4. And B2 is the matrix I get by taking A and replacing the second column with a solution vector. So 1, 3 times 3, 6. And the formula says that I'm supposed to be calculating determinants of those things, so I'll do that as well. The determinant of B1 is equal to 12 minus 12, which is 0. And the determinant of B2 is equal to 6 minus 9, which is -3. And Kramer's rule, so now I gotta bring out my sort of magic wand and cast Kramer's rule at this thing. What Kramer's rule says is that x is equal to the determinant of B1 divided by the determinant of A, which is 0 divided by -2, which is 0. Or sorry, by 2. Yeah, 2, which is 0. And that y is equal to the determinant of B2 divided by the determinant of A, which is -3 divided by 2.
Wait, why is it
Yeah, not negative
not
two.
-2?
Does that not have a -2
I
here?
thought you put negative.
Oh, I did. I said -2. Yeah, you're good. You guys are right. Okay, so what that says is, this is claiming right now, what Kramer's rule is claiming is that x is equal to 0, y is equal to 3/2 is a solution to that system of equations. And if we go check and see, let's see, 0 plus 2 times 3 halves is equal to 3. Oh, yeah, that worked. And 3 times 0 plus 4 times 3 halves, let's see, so that's 2 times 3 is 6. Yeah, that works. So yeah, it did it. Now, I'm not even sure that the book really explains why this works. This is essentially just a whole bunch of algebra piled up into a magic formula. This is not an efficient way to solve equations generally. But if you hate row reduction and you like determinants, Kramer's rule might be for you. So I actually saw Kramer's rule when I took Physics 143 here. I had a professor that insisted that we solve for particular values of current on branches of a circuit by using Kramer's rule. Because you could find out the current on a specific branch instead of trying to solve the entire current at the same time. This is a pretty fast way to pick up a specific value of a variable, even if you don't want to calculate the entire vector. Right. Okay, so that is everything that you need to know about determinants in one whirlwind go through. Tomorrow what we're going to do is I'm going to bring in a whole bunch of problems to work on. We'll sort of do regular workshop, quiz day. This is the last material that you are responsible for exam 1. So this is the cutoff right here. Anything next week is not part of the exam. I think that's probably plenty.